Welcome back. Today we're going to talk more about Cartesian tensors, their properties and some of the operations that can be performed on them. So to remind you, a second order tensor A with components aij can be expressed as aij times the unit dyads ei dyadic ej, and therefore in a different coordinate frame ei bar, the components would be aij bar, and we could write the tensor as aij bar, ei bar dyadic ej bar. These components between these two frames of reference transform according to the rule that we've seen before using the orthogonal rotation matrix M. So A bar would be equal to M, A, M transpose, and the inverse of that, converting from the new frame to the old frame, A equals M transpose A bar M. Now, let's recall the spectral matrix P, which we constructed from the eigenvectors and found that the transformation P transpose takes a matrix A and diagonalizes it, where the eigenvalues, lambda 1, lambda 2, lambda 3, are the diagonals of the matrix. And the components of P are the components of the three eigenvectors. In other words, P is a special case of M that transforms the components of the tensor A, assuming that it's symmetric, so that the components are diagonal. And the base vectors, the coordinate frame in which this is the case, are the principal axes defined by the eigenvectors, xi. So that suggests that for any symmetric tensor, we can always find a frame of reference in which the off-diagonal components go to 0, and all that are left are the diagonal components, which are the eigenvalues. And that frame of reference is defined by the three mutually orthogonal eigenvectors, which define the principal axes. And the eigenvalues along the diagonal of the tensor in this frame of reference are called the principal values. Hence, for symmetric tensors, we can think of eigenvalues as properties of the tensor, not merely properties of a specific matrix. And regardless of your starting point, if you can solve the eigenvalue problem, you can find the transformation that will take you to the principal axes by solving the eigenvalue problem. So all symmetric tensors can be represented in a coordinate system in which their components are a diagonal matrix. So let's consider some properties of tensors that we've already seen of matrices. So one of them is the transpose. So in the same way that we can take the transpose of a matrix, we can define the transpose of a tensor A to be aji ei by ej, or in a different frame of reference, aji bar ei bar dyadic ej bar. In other words, if you take the transpose of the matrix representing a particular tensor in one frame of reference, and you transform that to a new frame of reference, you'll get the transpose of the tensor components in that new frame of reference. Similarly, we can define a symmetric tensor such that A is equal to A transpose, or aij equals aji. So symmetry is not only a property of a matrix, but it's also a property of a tensor. If the matrix representing a tensor in one coordinate frame is symmetric, then the matrices representing it in every coordinate frame will be symmetric. So the same is true for skew symmetry. So a skew symmetric tensor would be defined as A equals minus A transpose. If we take the combination of tensors A plus A transpose, then this must always be symmetric, because the transpose of A plus A transpose would be A transpose plus A. Similarly, if we take the difference, A minus A transpose, then that tensor would always be skew or antisymmetric, because the transpose of A minus A transpose would be A transpose minus A, which is its negative. And it's simple to see that it's always possible to decompose any second order tensor into a symmetric part called sim A, which is 1/2 of A plus A transpose, and a skew part called skew A, which is 1/2 of A minus A transpose. And this is the so-called symmetry decomposition, and is useful in continuum mechanics, particularly when we look at fluids. Now, let's consider the invariance of a second-order tensor. If we recall that the trace of the diagonalized matrix of components would be the sum of the eigenvalues, lambda 1 plus lambda 2 plus lambda 3, so that would be the trace of PA, P transpose, or in index notation, PIR, ARS, PIS. And PIR, PIS, given the orthogonality of P, would be delta RS, and delta RS by ARS equals ARR, which is the trace of A. So you see that the trace of the matrix is also the sum of the eigenvalues, and since P is an orthogonal matrix, the trace is really a conserved quantity. So whether we evaluate the trace in one coordinate frame or another coordinate frame or the principal axes, it's always the same. It's always the sum of the eigenvalues. And so the trace of a tensor is a conserved or invariant quantity. So even though the specific components of the matrix change as we change our frame of reference, the sum of the diagonals doesn't. It's an invariant. So the trace, therefore, is not only a property of the matrices, it's really a property of the tensor. So we can write trace of A, which is a scalar, would equal trace of the matrix A, or trace of the matrix A bar, or AII, or AII bar. Similarly, we could prove the same thing for the trace of A squared, or trace of A raised to any power. So the trace of A squared would also be the trace of A bar squared, which would also be lambda 1 squared plus lambda 2 squared plus lambda 3 squared. So again, this is a property of the tensor. The same is true of the determinant. So the determinant of A will equal the determinant of the diagonalized matrix, which is the product of the eigenvalues lambda 1, lambda 2, lambda 3. And again, regardless of which frame of reference you measure the tensor in, the determinant that you calculate will always be the same number, and that will always equal the product of the eigenvalues. So the determinant is an invariant. So we say that a symmetric second-order tensor has three independent invariants. And you could think of these as lambda 1 and lambda 2 and lambda 3, but they're typically defined by the coefficients of the characteristic equation that we use to solve for the eigenvalue problem. Remember, for a 3×3 matrix, the characteristic equation is a cubic, for which lambda 1, lambda 2, lambda 3 are the roots. So the characteristic equation is the determinant of A minus lambda I is equal to 0. And we showed that that's equal to lambda cubed minus lambda 1 plus lambda 2 plus lambda 3 by lambda squared, plus lambda 1, lambda 2, lambda 2, lambda 3, lambda 3, lambda 1 times lambda, minus lambda 1, lambda 2, lambda 3. And we've now seen that that's equal to lambda cubed minus the trace of A times lambda squared plus 1/2 of the trace of A squared minus the trace of A squared times lambda minus the determinant of A. And since the trace and the trace of A squared and the determinant are really properties of the tensor, not the specific matrix, we can write that the characteristic equation is lambda cubed minus trace of a lambda squared plus 1/2 trace of a all squared minus trace of a squared times lambda minus the determinant of a is equal to 0. So these coefficients, trace a, 1/2 trace a squared minus trace of a squared, and the determinant of a are called the principal invariants. And so the trace of a is called the first principal invariant, I1. The second coefficient, 1/2 of trace of a all squared minus trace of a squared, is called I2, the second principal invariant. And the determinant of a is called I3, the third principal invariant. Next, we'll introduce a useful operation on a tensor, or a useful variation of the tensor, called a deviatoric tensor, or we sometimes talk about taking the deviator of a tensor. So the deviator of the tensor A is denoted A prime, and is defined as A minus 1/3 times the trace of A times I, the identity tensor. So in other words, what we've done is we've subtracted 1/3 of the sum of the diagonals from each of the diagonals. So component-wise, Aij prime is equal to Aij minus 1/3 delta Ij times Akk. So as an exercise, let's find out what the principal invariants of A prime are, the deviator of A. So you can probably guess that I1 prime, the first principal invariant of A prime, would be Aii prime, which would be Aii minus 1/3 of delta Ii Akk, which would therefore equal Aii minus 1/3 times 3, since delta Ii would be 3, times Akk, which therefore equals 0. So of course, by subtracting the 1/3 of the trace from each of the diagonals, then taking the trace, we get 0. I2 prime turns out to be a little trickier to calculate. We won't do the working here, but you should be able to show that it's equal to minus 1/3 I1 squared plus I2. And finally, I3 prime equals I3 minus 1/3 I1 times I2 plus 2/27 times I1 cubed. So we'll leave the proof of these results to you as an exercise. Next, let's talk about vector and tensor calculus. So you're familiar with the operations of vector calculus, and these can be applied to tensors as well. So for a scalar field phi, as a function of x1, x2, and x3, you know that the gradient of that scalar field is a vector that points in the direction of the greatest change. So grad phi equals del phi del xi by ei. So it's a vector with components being the partial derivatives of that scalar function with respect to each of the coordinate directions. For a vector field, A of x1, x2, x3, or ai of xj by ei, we can compute the divergence of A. And div A is a scalar defined by del ai del xi. This is a scalar because this is a sum. Del a1 del x1 plus del a2 del x3 plus del a3 del x3. The curl of a vector is computed from the determinant, where the first row is the base vectors e1, e2, e3. The second row is the derivative operators, del x1, del x2, del x3. and the third row is the components of the vector, a1, a2, and a3. So in index notation, this could be written as eijk, ei, del ak, del xj. And this is a vector field. The curl of a vector is a vector. You can see that the k's sum, and the i's sum, and the j's sum, but the i's are summing components of the vector, hence we get a vector. And this vector would look like del a3 del x2 minus del a2 del x3 would be the e1 component, the x1 component. Del a3 del x1 minus del a1 del x2 would be the second component. Del a2 del x1 minus del a1 del x2 is the third component. You can also use some of these operators on tensors. For example, the divergence of a tensor A is a vector. So the divergence of a vector is a scalar, the divergence of a tensor is a vector. And its components would be del aij del xi. So the vector would be del aij del xi by ej. This is an important operation in continuum mechanics. And another one that's related to the divergence is the divergence theorem. And so the divergence theorem is for the integral of the divergence of a vector field over a three-dimensional region R can be related to the dot product of that vector field and the outward normal n integrated over the surface. So the triple integral of div A with respect to volume over R is equal to the surface integral of A dot n integrated over the surface. So that tells us that the divergence of a vector field is the amount of the vector that is escaping the surface, that is crossing normal to the surface. And we can also apply the same theorem to the divergence of a tensor.